Hi everybody, Jonathan here. In this video, I'm going to be giving you my take on section 2.6, which is all about limits at infinity. So in the book, you can find the definition of a limit at infinity. It says that the limit as x goes to infinity of f of x equals L means that f of x can be made to be arbitrarily close to L by getting x to be sufficiently large. And if you think about it, this is actually the exact definition of the function having a horizontal asymptote on the right. Recall, the horizontal asymptote means that the graph gets arbitrarily close to the horizontal line. So in other words, the output values are getting very close to the value of y at the horizontal asymptote. And there's a couple pictures here of the limits of some function equaling the value L. And one more down here. It's a common misconception that a function cannot cross its horizontal asymptote, but as this example is trying to show you, a function can easily cross its horizontal asymptote infinitely many times. And the definition of the limit as x going to minus infinity of f of x being some number is really similar, and again, it just means it's got a horizontal asymptote on the left. However, one nice thing about this is that this is much more compact notation. It's far easier to do things with more complicated functions in terms of limits than talking about horizontal asymptotes. For example, things like the limit laws are going to hold for limits at infinity, whereas it would be quite awkward to say, well, if a function f has y equals L as a horizontal asymptote, and a function g has y equals m as a horizontal asymptote, then the function f plus g has L plus m. I mean, it's just a lot easier just doing all that with limits. So limits give us, it's the exact same idea of having a horizontal asymptote, but without all the geometric baggage, and it's something much easier to work with. Now, a lot of the problems that you're going to be asked to solve with these infinite limits are where the function is a rational function. And if you don't remember, a rational function is simply one polynomial divided by another polynomial. Now, the book and I do this slightly different. The book says basically pick out the highest power of x that appears, in this case it's x squared, and divide the top and bottom by x squared. I, for one, find it a lot easier if instead of dividing by the highest power of x, that you instead factor it out. So in this case, in the top, the highest power of x is x cubed. In the bottom, the highest power of x is x cubed. So I think it's easier to factor the x cubed out of the top and bottom. So in this particular case, we've got the limit as x goes to infinity of 5x cubed minus 2x squared plus 3x minus 4, all divided by 2x cubed plus 14x plus 7. When you factor x cubed out of the top and bottom, that becomes the limit as x goes to infinity of x cubed times the quantity of 5 minus 2 over x plus 3 over x squared minus 4 over x cubed end parentheses, divided by x cubed times the quantity of 2 plus 14 over x squared plus 7 over x cubed end parentheses. And at this point, having factored, it's now really easy to see that the x cubes just cancel. It's a lot cleaner, at least, than what the book does. And go ahead and cancel this x cubed, and we get that this is equal to the limit as x goes to infinity of 5 minus 2 over x plus 3 over x squared minus 4 over x cubed, all divided by 2 plus 14 over x squared plus 7 over x cubed. And it turns out one of the limits that you have to just know is that whenever you have the limit at plus or minus infinity of a constant over a positive power of x, that's always 0. So all these terms here that aren't constants, once you've got them something over a positive power of x, those all just go to 0. So you can then just immediately say that this limit is going to equal 5 halves. Now for a harder example. These exact same ideas can be used to find the limits not just of rational functions, but of what I like to call radical functions. Radical functions are stuff built out of polynomials, but also with radicals thrown in. For example, a square root or a third root or any type of root. So this is a radical function, and in it we're going to find the limit as x goes to minus infinity of the square root of 3x squared minus x plus 2, all divided by 2x plus 11. So you can use the exact same idea. You look for the highest power of x that shows up. In the top it's x squared, and in the bottom it's x. So you factor x squared out of everything, however, inside the radical in the top. And the top becomes the square root of x squared times the quantity of 3 minus 1 over x plus 2 over x squared. Whereas the bottom, the highest power that shows up is simply x. So we can factor that x out and get the bottom to be x times the quantity of 2 plus 11 over x. Now, it is a fundamental property of square roots that square roots are multiplicative, which means that if you have a square root of a product, like we do have here, x squared and all this stuff in parentheses, that is equal to the product of the square roots. So the top can now be rewritten as the square root of x squared times the square root of 3 minus 1 over x plus 2 over x squared, whereas the bottom stays the same for now. Now this is the trickiest part that often gets students the most. The square root of x squared only equals x when x is positive. If you think about it, if x is negative, when you square it, it's going to become positive and the square root will stay positive. So it can't possibly equal a negative number. A square root is never going to equal a negative number. So in order to simplify something like the square root of x squared when x is negative, and since we're taking the limit as x goes to minus infinity, you have to put a minus in front. Since x is negative, minus x will be positive. So square root of x squared, it simplifies to minus x if and only if x is negative. At any rate, we now get this to be the limit. So we get minus x times the square root of 3 minus 1 over x plus 2 over x squared, all divided by x times 2 plus 11 over x. And these x's cancel, so we get the limit as x goes to infinity of minus the square root of 3 minus 1 over x plus 2 over x squared, all divided by 2 plus 11 over x. And once again, all the stuff that is a constant over a positive power of x, that limit will be 0. So you can go ahead and just ignore all this stuff. Again, it's the limit laws that allow us to take the limit of each of these pieces separately. But at the end of the day, only the constants survive. So we wind up with the final answer of being minus the square root of 3 over 2. Okay, so that is fine. That's basically the technique for finding the limit of rational or polynomial functions. However, there's a lot of other limits at infinity that you more or less just have to know. If you understand the functions well, then you just know what the answer is. There's no work to do because you know that that particular function has a horizontal asymptote or not. So the first one, which you've already been using, is that the limit as x goes to plus or minus infinity of 1 over x to the r is 0, provided r is positive. And you can tell that by looking at the graph. The graphs of any function like that is going to have this overall shape, and you can tell that it's got y equals 0 as a horizontal asymptote as both on the right and on the left. Now, other important limits is the function f of x equals e to the x, or for that matter, any positive base to the x. The graph will basically look like this, and that tells you the interesting one here is the limit as x goes to minus infinity of e to the x is 0. So long as you know that, if you know e to a big negative number is going to be very close to 0, that'll help you figure out a lot of limits. And the limit as x goes to infinity of e to the x is infinity. It's not hard to convince yourself that this gets arbitrarily large over here. Now another function that students often have trouble with the limits of, because again, it's just something you pretty much have to know the graph and the limits. There is no work to be done. When you're asked to find a limit with this type of function, you just know it. Or don't know it if you're unlucky. So from the graph, this is the graph of y equals natural log of x. And from the graph, we get that the limit as x goes to 0 from the right of natural log of x is equal to minus infinity. So this isn't a limit at infinity, but I think it's nice to include here for completeness. And the other thing that's important to realize is that the limit as x goes to infinity of natural log of x is equal to positive infinity. That's kind of hard to see from the graph. Here, you can try and follow the graph over, and while it gets flatter and flatter and less steep, it's really not that clear if it's ever going to level off or not. However, natural log of x is the inverse of e to the x. And since e to the x, you get the graph by flipping this over, the inputs of e to the x get arbitrarily large. E to the x you can put in any big number, which means the outputs of natural log of x also get arbitrarily large. Now the last function whose limit you just need to know is arctangent of x. Be a little bit careful here. A lot of people use tangent inverse to mean the exact same thing as arctangent. However, that notation is confusing because usually when you do tangent to a power, you just mean the regular tangent function to that power, whereas tangent to the inverse is different and refers to the inverse function, which is not at all the same as 1 over tangent of x. So I always use arctangent. So this is the graph of arctangent because it's just one piece of the graph of y equals tangent x between minus pi over 2 and pi over 2 and flipped about the line y equals x. Since tangent of x has vertical asymptotes at minus pi over 2 and pi over 2, arctangent of x is going to have horizontal asymptotes at y equals minus pi over 2 and y equals pi over 2. So therefore, the limit as x goes to minus infinity of arctangent of x is minus pi over 2, and the limit as x goes to infinity of arctangent of x is equal to pi over 2. So again, these are all limits. You'll encounter them in more complicated problems, but when you see them, you just have to know their behavior when x is either very large or very large negative, and that's how you have to do those problems. You generally don't do it algebraically like we do for rational or radical functions.